Hello everyone. Today we'll be covering Thermodynamics Lesson 4, which is the first law of thermodynamics. The first law states that energy cannot be created or destroyed, only transformed from one form to another. This is also known as the conservation of energy. This means that if I cannot just simply pull energy out of thin air. It's not possible. I have to do something that then becomes that energy. For example, if you were to clap your hands, you're putting in kinetic energy into your hands. When they hit together, that creates the sound you hear, puts energy into the air that causes it to vibrate. And if you go hard enough, you'll notice your hands get hot. That kinetic energy was turned into more kinetic energy of the air vibrating, creating the sound, and heat. Therefore, the energy just simply changed. Well, same thing in thermodynamics. I have energy pumping into a system, and that energy has to add up to something. It can't just disappear. Well, that's termed as the change in energy of a system is equal to the energy that crosses the system boundary. Now, you may ask, well, what is a system boundary? Well, system boundary is whatever you're studying. It could be, say, I'm studying the heat transfer through a flow duct in your ventilation system, or through pipes as they're going through your refrigerator. Or I am, for example, doing a car engine. I want to know what happens to the gas in the air when it's going up and down. Well, you have two types of systems I described, a closed system and an open system. We shall first cover a closed system. A closed system is known as constant mass. Means no matter what happens to the system, the volume can change, the pressure can change, anything can change, except how much mass I have. So if I have 5 kilograms of, say, oxygen at the beginning of my process, for a closed system at the end, I still have 5 kilograms of mass. It may have changed into something else, but there's still 5 kilograms of mass. So I need to create first my system boundary. If I say I have some fluid in here, let's say water, H2O, and it's under some pressure. And this is a piston. So the piston is going to have some cross-sectional area, A, and this is the same piston, simply moved upwards. So if you remember from coordinates, since I have an area at Y, no, this is X. I was right the first time. X, Y, Z, I have my K hat, J hat, I hat. Well, what energy is going to go into the system? What energy is going to leave the system? Well, I can always pump heat into my system. That can cross my system boundary. Remember, my system boundary is the mass. So at state 1, when the piston hasn't moved, this would be my system boundary, encircling the entire mass. Now, after it moves at state 2, well, I had a change in volume. Therefore, my boundary is going to expand, but it still encompasses the entire fluid. So now my boundary is up here. Oh, but it still encompasses, if I could draw well, the entire fluid. So what energy is going into the system, what energy is leaving the system, and so forth? Well, you have work and heat in a closed system. All right? The vapor or the fluid might do some work. It might move some part. Well, to move a part, you have to pump energy into that part to get it to move. Well, that means energy is leaving that fluid. And if you're pumping heat into the fluid, you're then giving energy into that fluid. You're adding to it. So your equation would be your change in energy of your system would equal the heat pumped into the system minus the work done by the system, or by the fluid. Well, what is work? How do I calculate that? Well, remember work is equal to, by the way, W is work, Q is heat. Work, W, is equal to, from 1 to 2, the integral of the vector F dotted with your displacement vector. So, and it's commonly denoted as work from point 1 to point 2. Well, I don't have a force on my system. I do have a force, but I don't know what that force is. How do I find it? Well, if you recall, the force vector is equal to the pressure of the system times the area of whatever surface it's acting on and in the direction that the force is being applied. In this case, vertical, because the fluid is going to push the piston up. Well, plug that in. I have work from 1 to 2 is equal to the integral from state point 1 to state point 2 of pressure times area times dz. Because remember, with K, I'm pushing the piston up. I classify that as the z direction. Well, if you notice, dV is equal to an area times an incremental change in height. So you get work from state point 1 to state point 2 is equal to the integral from 1 to 2 of P dV. Now, if pressure is constant, it's just going to simply be pressure times your change in volume. Pull it out of the integral. If pressure is not constant, well then you're going to need some sort of function that defines what's happening to your system. And if your volume is constant, well, if my volume is constant, dV is 0, so there's no work done. So P is constant. You get work from 1 to 2 is going to equal pressure times V2 minus V1. If V is constant, no moving parts, so work 1 to 2 is equal to 0. Now what if P is not constant? Well, I need a function. You need some sort of function. You need function for P. And it could be a polytropic process, might not be. It's up to your system, whatever can happen. So then, well, what about heat? How do I find the heat? Well, this is how you find heat, or Q. You'll either be given it, say the piston's over flame, the fire gives 1,000 kilojoules of heat into the water to boil it. You could be like, okay, this fluid changed from liquid to vapor at these two state points. How much was the change in internal energy? Well, you could find your change in energy from the tables. You could have your change in energy from how much heat you have to pump into to change from fluid to vapor. But it would have to either be given to you or you could find it through heat transfer. But that is a different course, so that will not be covered in this lesson, so we're going to say it is given. Or calculated by given the work or the change of internal energy. Well, remember I said there were two types of system, closed system and open system. Well, what is an open system? Open system. Well, in an open system, you have a constant volume, but not a constant mass. Means my mass can flow through the entire system, it can change, that type of stuff. Well, the simplest one is I have, let's say, some box. Something is happening inside this box. And I have some amount of mass flowing in at some rate. I have some amount of mass flowing out at some rate. I have some amount of heat being pumped into the fluid at some rate. And I have some amount of power being done by the fluid at some rate. Well, how do I analyze that? Well, you'll notice these are all rates. So instead of a delta E, well, now you have to check how energy changes with time. So it becomes dE dt is equal to the heat pumped into the system as a function of time minus still the work, or the power in this case, because it's a derivative of work, Now, what happens with the mass flow rates? Well, when mass is flowing into the system, it has some sort of energy that it brings with it. And when a mass leaves the system, it has some sort of energy that it takes with it. Well, how do you quantify that? You quantify that as a plus the mass flow rate into the system times the change in enthalpy going in plus the kinetic energy coming into the system plus the potential energy coming into the system minus the amount of energy or the amount of mass leaving the system times the enthalpy of that mass, the kinetic energy of that mass, and the potential energy of that mass. Now, there's two keywords that you need to look for when you're solving open system types problems, because this can get really complicated. As you can see, I have derivatives all over the place. Well, you want to look for what is the terms are called steady state. If a system is operating at steady state, that means the energy of the system does not change with respect to time. Therefore, dE dt equals 0. And that simplifies your system a lot because now you can write your first law equation for an open system as 0 is equal to the heat pumped in minus the power taken out plus mass flow rate in times enthalpy in plus kinetic energy in plus potential energy coming in minus the mass flow rate leaving the system times the enthalpy it brings with it, the kinetic energy brings with it, and the potential energy brings with it. And with steady state, that should also mean that the mass flowing in equals the mass flowing out, which means these two are now the same. So your equation simplifies easier into 0 equals Q dot minus work dot plus the mass flow rate times H in minus H out plus kinetic energy in minus kinetic energy out plus potential energy in minus potential energy out. These two equations here, this for an open system at steady state, so this is the general equation for the first law of an open system, and this equation here is the first law of thermodynamics of a closed system. Now we shall do some problems, and I shall join you shortly. Hello everyone, here will be our first example of using the first law of thermodynamics, and we shall be doing a closed system. So I have here a piston, and inside the piston, there we go, some piston, and beneath the piston is some water that I'm heating up. At the beginning, my water has a volume of 0.1 meters cubed, a mass of 0.5 kilograms, and has a pressure of 4 bar. And my final state will be a temperature of 300 degrees Celsius. I want to know what is the work done by the fluid and what is the heat. Well, first things first, I need to know where I am. Where is my water liquid? Is my water vapor at the beginning? Is it just in the middle of transferring from liquid to vapor? Where am I? What's my state point? Well, let's first off by find the specific volume. Remember, we need two independent intrinsic properties. So my specific volume is 0.1 meters cubed divided by 0.5 kilograms, which is equal to 0.2 meters cubed per kilogram. Now, unfortunately, I was not able to pull up a table for this computer, but I found one on paper where when the pressure of water is equal to 4 bar, the specific volume of the fluid, saturated liquid, is 1.08 times 10 to the negative 3 meters cubed per kilogram, and the specific volume of the vapor is equal to 0.4625 meters cubed per kilogram. Well, my specific volume is between the saturated vapor, and saturated fluid. Therefore, I am transitioning from liquid to vapor. I am inside the dome. Well, now I know where I am. So, let's do the equations. The work from 1 to 2 is equal to pressure times the change in volume. And P dV. Now, is my pressure constant or is my pressure changing? Well, here's the thing with pistons. Pistons will move as the pressure increases. It's simply going to push it up unless there's something pushing back. Well, if it's moving with the system as it expands, that means the pressure must be constant. Therefore, pressure is constant. My work equation will be pressure times V2 minus V1. Now, you'll notice this will result in, if you do unit analysis, kilojoules per kilogram. Well, I'm asking for work. I need it in kilojoules. Well, to do that, I multiply by the mass. So, to find the work, I will have my equation as work from 1 to 2 is equal to the integral from 1 to 2 of the mass times the pressure times the change in volume, which will equal the mass times the pressure times V. Well, I'm sorry, I was wrong. This will result in kilojoules. But remember, I am dealing with specific volume. Therefore, if I do it with the values I have, this equation actually becomes the integral from 1 to 2 of P dV. Well, to turn it from specific volume into volume, you'll have to recall that this would then become from 1 to 2 P pressure times the mass times then the change in specific volume. This will give me kilojoules. Okay, well, like I said earlier, because it's a piston, pressure is going to remain constant, and the mass is constant because I'm in a closed system. So I get the work from 1 to 2 is equal to the pressure times the mass times V2 minus V1. Now, what is V2? Well, V2 is the specific volume of water at 300 degrees Celsius and at a pressure of 4 bar. At 300 degrees C and at 4 bar. Well, you would have to look that in a table or interpolate or do whatever you need to get that value. I have it here as V2 is going to be equal to 0.699 kilograms. No, it's a mistype. 0.699 kilo. Oh my god, I'm sorry. I'm so sorry, guys. Volume. Meters cubed per kilogram. So, my work from 1 to 2 is equal to my pressure, which is 4 bar, which I actually have written out here. So we'll have to convert that to pascals. That'd be 400 kilopascals times 0.5 kilograms times 0.699 meters cubed per kilogram minus 0.2 meters cubed per kilogram. So the work from 1 to 2 is equal, plug it into a calculator, you get 100 kilojoules. So this is work 1 from state point 1 to state point 2. Now, how much heat is being pumped into the system? Well, if you recall from the first law of thermodynamics, delta U is equal to Q minus work. Now I know what my work is because I just found it. I don't know what my Q is, I'm trying to find that. But what is my change in internal energy? Is there a way for me to find that? Well, there is. Remember, if you have two intrinsic properties and they're independent, you can find all of your properties of the system. So since I know where I am for my state 1, I know my internal energy at state point 1. Since I know where I end up, I know my internal energy of state point 2, which my internal energy of state point 1 is 2,805 kilojoules per kilogram would be my specific internal energy at state point 1. At state point 2, no, I'm sorry, that is state point 2. At state point 1, my internal energy is 1,455 kilojoules per kilogram. At state point 2, my specific internal energy is 2,805 kilojoules per kilogram. Well, let's plug it in. Remember, these are specific internal energies, so I need to multiply by my mass. So I would have my mass times specific internal energy 2 minus specific internal energy 1 is equal to the heat minus the work. Simply solve for Q. So let's solve for Q. Well, you get Q is equal to M times U2 minus U1 plus the work. So Q is equal to 0.5 times 2,805 minus 1,455 plus 100. This is equal to 5 minus 1,455 times 0.5 plus 100. This is equal to 775 kilojoules. Therefore, my heat from process 1 to 2 is equal to 775 kilojoules of heat added. To review, what happened was state point 1 and state point 2 were given. First thing I did is find out where I am in state point 1. I did that by finding the specific volume here and the pressure, and I was able to determine that I have some sort of quality. Did I care specifically where I was? Well, I did care for finding the internal energy at state point 1, so you do need to determine your quality. And you'd have to do some interpolation or use some of the quality equation in some way, shape, or form. At state point 2, I was told that I'm going to end up at 300 degrees Celsius, but I did not know any of my other properties. But I was told that the piston, I'm moving a piston. Well, if you're ever moving a piston, you're going to have constant pressure. Therefore, I know my temperature, I know my pressure, I am able to find out all my other properties. Once I found out my specific volumes, and I knew what my pressure was constant, I was able to find the work done by the fluid. Once I knew the work done by the fluid, I could then use the first law of thermodynamics to determine the heat that was pumped into the system. And since I knew what my two state points were and where they were, I was able to gain the internal energies of the system, plug those into the first law equation, solve for Q, and determine my heat. Thank you very much. If I were to do an open mass system, the only thing that would change, everything's exactly the same, except you recall, I now have these enthalpy values. What you'd simply do, get them out of the table. You would see where I am on state point 1, you'd go to your table, get that enthalpy value, plug it into this equation. Same with the exit. Almost nothing changes. You're just doing an extra step. Thank you very much and have a wonderful day.